Greetings, friends of chemistry. Martin and I are doing the review.
I think you mean Mom and I, young man. What are you trying to do? Take my place? I am clearly the mother here. You can tell by my hat. No one could possibly impersonate that. Clearly.
Yeah.
So.
Hello, friends of chemistry. Martin and I are doing review questions 4 now.
Yo, greeting.
Module 15. Okay, it looked nothing like a beard. It wasn't even close. I had no idea I was going to try that. Though. Yeah.
My beard is
I should get your Bjorn beard from the attic. Okay.
That would take too long.
Review question number 4.
After taking a cursory glance through a chemistry book, a student says that sometimes a chemical reaction is written with a single arrow and sometimes it is written with a double arrow. The student says that this means some chemical reactions are equilibrium reactions and some are not. What is wrong with the student's statement?
What is wrong with the student's statement, Martin?
Well, it does, just because it only has a single arrow doesn't necessarily mean it's not in equilibrium.
Do all chemical reactions reach equilibrium?
Yes.
Yes.
So if we have an arrow and assuming the equation is balanced, then it is in equilibrium. Why is there a difference between the 1 arrow and the 2 arrow?
Well, excuse me.
Just to emphasize that they are to be read as in equilibrium with.
What happens if the K is humongulous?
Then the equilibrium is weighted.
Humongulous is a scientific term that you should all
super scientific. Humongous.
All right.
When K is large, the equilibrium is weighted towards the product side of the equation.
Right. So let's look here on page 499. Okay. So the equilibrium constant for a reaction, when it's really large, the reaction is weighted toward the product side. So when equilibrium is achieved, there's lots of products and very few reactants, right? So if the equilibrium constant for a chemical reaction is very large, then that equilibrium is heavily weighted toward the product side of the equation. At some point, the equilibrium constant becomes so large that once the reaction has hit equilibrium, there are mostly products and virtually no reactants present. And chemists say that the reaction is so small we can just ignore them. And so when the equilibrium constant is very large, we replace the double arrow with a single arrow, indicating that as far as we're concerned, the reaction completely runs out of reactants. And the equilibrium constant is very, 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 very small. Teeny. Another scientific term.
You shouldn't lower your volume for that.
Teeny, teeny, weeny.
That's right.
We write the reaction in reverse. From now on, then, when you see a reaction that contains a single arrow, remember that the reaction is in fact in an equilibrium. But the equilibrium is so heavily weighted toward the product side that we just assume there are no reactants present when the reaction finishes. Okay? So the answer is when we have an extremely large K. What was the scientific term? Humongulous?
Yes.
A humongulous K. The reaction is so heavily weighted toward the product side that at equilibrium that at equilibrium we assume are no reactants left because the amount of them is so small. Okay. So you can be confident that on the test there will be a similar question. So make sure you understand this. If you don't understand this, make sure you ask me about it so I can help explain it.
Okay.
Number 5.
Why do we ignore solids in the equilibrium constant and when using Le Chatelier's principle?
Good. So
How's my accent?
Le Chatelier. Le Chatelier is fine. Yeah.
I said
American.
Le
No, you said it
Chatelier.
beautifully. You would normally not pronounce the R.
The D is silent.
There's no D in it. Le Chatelier.
Prove it.
Okay. So if we look on page 508, what does it say?
Le Chatelier's principle ignores solids and liquids as a source of stress to the equilibrium.
Why?
Because it doesn't stress the equilibrium.
Well, what are we looking at when we're talking about the reaction rate? What's those little brackets mean? It means
concentration.
the concentration.
But solids don't have
Correct.
concentration.
They don't really have concentrations. Gases can, aqueous solutions can.
It just doesn't work that way.
Okay?
It doesn't have concentration. Like you can have particles of solids in solids, but it doesn't count as a concentration.
So what two phases do we ignore in the reaction?
Solid and liquid.
Right. We do not ignore aqueous and gas, right?
Because those do have concentrations.
Right. So the amount of the solid can change without the concentration of it changing, right?
Yeah.
It's still the same concentration. There's just less or more of it. So for number 5, we're going to write the concentration of solids remains constant. Even if the amount changes. Okay, so now we're going to look at number 6, and then we'll stop the video and start a new one for the rest of the questions. Can you read it?
Why are acid ionization reactions important in chemistry?
Okay, so what are acid ionization reactions?
It's
Let's see, where do we explain them here in the book? I'm having trouble turning the page. Okay, so on page 514, the text defines acid ionization reaction as the reaction in which an H positive separates from an acid molecule so that it can be donated in another reaction.
yeah.
So an acid that is a strong acid will do what?
It's going to.
So what are we looking for in the acid ionization reaction?
Reaction. In
What
which
becomes an ion? What's the ionization?
H plus.
Yeah, so the H positive is going to break off the rest of the acid, okay?
Yeah.
So the question is asking us, why are they important in chemistry, okay? So what does it mean to be a strong acid versus a weak acid?
A strong acid.
This will happen really easily with a strong acid.
Yeah.
It will break off, right?
Yeah.
But a weak acid, it won't. They give the example of hydrochloric acid and acetic acid on page 514.
Lemonade doesn't kill
Yeah, because it may have a strong pH, but it's not a strong acid, right?
you. Okay.
So it's a weak acid. It's not going to, if you leave lemon juice on your teeth, you can damage your teeth because it's an acid.
I don't see how you could. Like when you
If
automatically
you sat there with the
swallow
lemon in your
or-
mouth for 2 hours, you could damage your teeth,
I see.
okay? Because the acid can eat away at the enamel. But it's not the same as, other acids,
Sulfuric acid.
right? Yeah, you can't leave.
The stuff in
You
your
can't leave
stomach.
hydrochloric
Stuff
acid in your
stomach is
mouth.
Bad stuff. Bad
So,
juice.
yeah.
Juice,
Okay.
yeah.
So the acid ionization reaction tells us whether it's a strong or weak acid, okay? What if it's, so we're looking at the constant, the K, right?
Yeah.
K, Ka, right? K subscript A. That refers to the acid ionization constant. So it's the equilibrium constant, okay, that we've been talking about, and it tells us what is the constant for the ionization reaction. If it's very large, then we have a what?
The stronger the acid. The larger the ionization constant, the stronger the acid.
Right. So that's a general statement, but that's as good as we need for our high school chemistry course. Okay, so that's it for question number 6, was that?
Yeah.
And we'll see you with question number 7.